Welcome to my YouTube channel. Today I want to discuss about limiting reactant. We talked about mole concept in a previous video, and we told you that if we have A plus B giving you C and D, and if you are provided with any one of components of the reaction, you could compute essentially any other based on the information that you just have, like the molar masses, and you have the coefficients, so you could do molar ratio, and you could move on to any of those and then compute how much grams of B is needed, how much of C would be produced, and how much of D would be produced. And for the products, we'll call them the theoretical or the maximum amount. Okay, what if a problem gives me this and this and wants to ask me how much of C or D is going to be produced, like two of the reactant? Now, if you have two of the reactant that is being provided for you, the problem is called a limiting reaction. Okay, it means just when you bake a cake, if you need 2 eggs and 1 cup of milk, let's say, here, if you have 3 cup of milks and 4 cakes, one of them is going to be extra a little bit. Okay, if you need for 2 cakes just 1 cup of milk, then for 4 of them you would just only need 2 and you would have 1 extra. Okay, it means you would have a little bit extra of one of your reactant, and one of your reactant is going to be finished up. The one that finishes up, or you run out of it, is called the limiting reactant, and the one that you actually have extra, we call it excess reagent. Okay, so for a limiting reaction, we have to actually make a table, and we cannot judge the amount of moles based on a simple strategy of going from A to C, because we don't know if A is important, is the limiting reactant, and or B is. So first we have to find out. To answer that question, we're going to take the amount of the reactants, convert them to moles, and then we will produce a table based on the moles, and that table would give us every information. But to work with the table is important, so I'm going to show you here through examples how do I form a table, table of moles, so to speak, for a limiting reactant story. Okay, and how do I use it? Okay, basically, if you calculate the table, from the table you could actually derive every component of the reaction that you need, and you're going to be able to answer any question. Let's just go through a very simple example. If I have Fe plus CuSO4 giving me Cu and FeSO4, you could see that it's 1 Fe, 1 CuSO4, 1 Cu, and 1 FeSO4. So for starting the problem, I have actually done a very simple problem to start with. Okay, I need the molar masses before I do anything. 51.8, 159.6, 63.5, and 151.9 gram of every of those, the molar masses of every of those compounds. Okay, if the problem tells you that you have 20 gram of iron and 40 grams of copper sulfate, and it asks you that how much of this or how much of this would be produced, or which one is limiting reactant, or how much of the excess reagent, because one of them is going to be the excess reagent, how much of that would remain. Okay, what should we do? The first thing that you do to convert these, like the 20 divided by 55.8 to moles of Fe, and also the 40 divided by this to give you moles of CuSO4. And if you do so, the grams, that's again the formula, mass divided by the molar mass. Okay, they give you the moles, number of moles. M divided by M gives you number of moles. Then this M I do at kind of italic form to let you know that's my molar mass, the ones in red. Okay, that the problem would provide for you, at least if you're if for these videos that I'm not want to waste my time on calculating these one more time. Those are just information that you could take from the periodic table. 20 divided by that would be 0.35 0.24, and 40 divided by that is 0.2506. Then I do form a table that goes from reactants to products. On the top line of that table, I would actually provide my molar masses, my coefficients. Let's say 1 mole of this, 1 mole of that gives you 1 mole of Cu and 1 mole of FeSO4. So these are those compounds one by one. Okay, and literally for the first one I just decided to use a simple case where you have no coefficient, or actually one coefficient for every compound, so it's very simple to do the table. We will do more complex examples as we go on. Let's just do one more example on this. So here in my table I would have columns for every one of those compounds. First I put the available amounts. This is the amounts that we have available, so we call them the available amounts. For Fe I have 0.3584. For copper sulfate I have 0.2506, and I circle them because I want to know which one is the available amount. Okay, so that's my available amount, and then I go to these spaces, one here and one here, and I provide different rows for them. Like one row for my available amount of Fe with blank all the other components, and one row for the available amount of CuSO4 with blank spaces for every other component. Now I'm going to see what if I use this much Fe, how much CuSO4 would be needed, and I will judge. And then if I use this one, and I would judge how much of Fe would be needed if I use this. How do I find this? It's just a ratio table. So I take this one, and I look at this line in the red. This we call the reference line. Reference line is very important, and that is because every time you want to judge a blank number, you're going back to your reference line. So this means with these two numbers and these two numbers, I'm going to compute this. This means the diagonal divided by the other number. So this times 1 divided by 1, it would be itself. So this would be 0.358. Okay, 84 actually. And this is more than I have available, so this would be your excess. And with your excess, you take this minus this to actually compute how much excess you will have. Okay, and my bad. This is the amount of the excess that you would have. Okay, for this one, I just go to the reference line again, and this would be now these two numbers and these two numbers. So again, the diagonal one. This time, this is this one. Times this divided by 1 again, and that would also be 0.2506. Okay, here I made a bad judgment. That's what I was stuck for a moment. The judgment here is you have this much available, but you need this much. So this is going to be limiting reactant. It means you don't have this much, you only have this much. But this, it means that, so this is the needed amount, and this is the available amount. We circle the available amount every time from the first step to actually make sure that we do a good judgment. So for this column, you need this much, and the available amount is more. So if you take, it would be, you would have extra iron in your problem or in your situation, and that would be this divided, this subtracted from this, and that would give you this much of iron. That would be extra iron. Okay, and then you make a very crucial judgment to move on. You look at the column that has your limiting reactant. This is the column that has limiting reactant, and you go, so that's the column, and on that column you look for the row that has the circled amount or the available amount. So that would be this column, the column of limiting reactant, and the row that has the available amount, the circled amount. and that would be the row that would be decisive in your calculation. So this would be this one, and I would continue to do the same thing with these numbers to find the blanks of the products as well. For any limiting reactant problem, you have to compute the products as well. Here again, I have 1. If you have the same number on your reference line, this means these numbers would also be the same. Or you could do the ratio, table ratio if you wish. You could say for this one it's 1 and it's this times 1 divided by 1, and for this that's the exact same story, but instead of this one it says with this number here, that is also a 1. Okay, we will also do a reference line that have other coefficients so that you could see how we do the ratio table. The ratio table is just the 4 numbers that you choose, and then if this one is x, you just say the diagonal divided by the other number to find x. Now you know that this is your excess, this is your limiting reactant, this is how much Cu you have, and this is how much FeSO4 you have. The problem is asking me to calculate the amount of grams of FeSO4, so I'm just going to take that, and this is, by the way, when you complete the table, you have all these numbers, and you're going to actually get the moles. You have moles them times the molar mass should give you grams, and the problem is always asking you for grams, okay, for M. So you have to multiply it by the molar mass from the table to get to your final answer. Okay, let me just use another color here just to make sure that you understand that you cannot actually provide moles. That's the problem that many students do. You cannot take this and say, okay, that's the answer. No, this is just the moles. You have to multiply by the molar mass to give me the answer. So this times the molar mass would be just 38.1 gram of FeSO4. If the problem asks you how much of Cu, then you have to do the same thing, this number, this time by the molar mass of Cu, and that would be 15.9 gram of Cu. Limiting reactant means you don't have anything of it, so 0 gram of CuSO4, that's the limiting reactant. Usually no one asks for the limiting reactant amount because that would be 0, so that's kind of stupid. They would ask what is the limiting reactant, and you have to say, okay, this one is the limiting reactant. Everybody knows that it's going to finish up, so you would have 0 grams of it. But for the excess, they may ask what is the excess, so you should provide Fe, or they may ask how many grams of excess is provided, is actually left after the reaction is done. So that's this amount, the subtraction, 0.1 times the molar mass, and that would be 6.0 gram of Fe would actually remain. So you could see that from the table you could actually compute any amount that you are interested to calculate. Okay, so that's this. Let's move on to yet another problem. I think we will have enough time to do yet one more problem in this limiting reactant, and then I probably post another video doing more examples on limiting reactant, because this is very important and everybody wants to actually know how we do if you have different coefficients and it's a little bit more complex. Okay, so I will probably do more of these problems on the next video, but let's just do this example and wrap up. Now this example is going to contain empirical formula in it. My bad. Percent yield in it. Sorry. So Na2SO4. If I cannot touch these small beakers that are going to spill over and make me mad. Let's see. Now I have these this kind of reaction. I have 1 mole of this, 2 moles of this, 1 mole of this, and 1 mole of that. So that's a little bit more complex because I have 2 moles of this. Okay, so I have to have another table that actually gives me different numbers. So, and let me just also write down the molar masses: 121, 40 grams, 58.3, and 140. 140. I don't know, it makes me mad when it's just wasting the time. So let's say the problem says 100 grams of this and 70 grams of this 100 grams of magnesium sulfate and 70 grams of sodium hydroxide is going to react, and the problem is asking if 39 gram of this is produced, what is the percent yield? So definitely it's a limiting reactant problem because it's giving me two of the reactants. So I could provide a periodic table that I could just give me every moles of the one that remains and moles of the products as well. So I have to provide a table, and before doing anything I just convert my grams to moles. Moles of magnesium sulfate and 70 divided by molar mass, moles of my sodium hydroxide. So this would provide you 0.831 and this gave you 1.75. Then you do a table. On the top for your table you would have the numbers, coefficients, 1, 2, 1, 1. And this one is magnesium sulfate, this one is NaOH, this one is magnesium OH2, and this one is Na2SO4. Okay, I just didn't have enough space here to do Na2SO4, but this guy is Na2SO4, so I already apologize for that if it's not very good written. So let's go on and also make sure that we have enough columns here, and we use our available amount of magnesium sulfate here, so 0.831, and available amount of NaOH 1.75, and we go about these blank things again. Anytime we put an available amount, we just provide an entire row for it. So I'm going to go for about this blank. It means now these two numbers. Okay, so this times 2, the diagonal, divided by the other number. If I do that, I would find that I would need 1.662, and I do have extra. So I could subtract and tell, okay, 0.088 grams, 8 moles of NaOH would be extra. For this one, this blank, again, that's two numbers and these two, so it would be the diagonal again. So we just kind of, you could do this and it's useful if you just ignore. Let me just get this lighter here, and I could use that to actually, if you do it on a test or on your notebook or at home, it's also useful. You kind of ignore the other row that you don't want. So this times 1 divided by 2, and that gave you 0.875. You need 87, but you have 83, so this is definitely the limiting reactant. Okay, so you go with the column that have the limiting reactant, and on that column you go with the row that has the available amount, that is that row. Okay, so I want to ignore the other one, ignore this, and just go by that one to get the available amounts. Okay, for the amount of the product. So if I just concentrate on this again, if you have two numbers in a row, you could use either one. Okay, this is just easier for me to use this because I have the same number on the reference line. So that would be this times 1 divided by 1. I don't have to use my calculator, it's easier to just use that. If you have same numbers on your reference line, just use that number instead of doing the calculation. I of course can use this and say this times 1 divided by 2, and I would get exactly the same number. That is also the amount of moles of Na2SO4. So I would have this much mole of NaSO4, this much mole of magnesium hydroxide, this much will remain from NaOH, and also 0 from magnesium sulfate. Now the problem is asking me for, I believe, let's do the problem first, and then I also want to extend to actually do a full solution of every other information that we could get possibly from this problem. This is also one thing that I do really want to do, because it's always this come to me, is there any other question that somebody can ask about this problem? I tell you yes, there is. So first you have to understand the problem fully, once you do that, or once you do the practice and you understand the problem fully, then you could address the small questions like the problem that it says, what is the percent yield if only this much is produced? Now, I do know that if I go to magnesium hydroxide and take this multiplied by 58, it would give me the theoretical yield or the grams for my magnesium hydroxide, and that would be 48.4. Okay, grams of magnesium hydroxide. If you take that 39 divided by 48.4 times 100, it would give you the percent yield that you're looking for, and that's the answer of the problem. This much percent. Okay, 80.58%. That's the answer. Now, what else can I understand? I could compute how many grams of sodium hydroxide would be excess. This times 40. I think this is also one thing that the problem is asking for, and it is 3.52 grams of NaOH would also be would also be left over from NaOH. How much of Na2SO4 or sodium sulfate would be produced? Again, you could take this time times 142, and that gives you 118 grams of sodium sulfate. So these are all the informations you could get. You could find that sodium sulfate, this much, 180 grams of it would be produced. This much is the maximum amount, or the 48.4 grams of magnesium hydroxide that could be produced. Also, this much would be left over, and 0 grams, of course, it's going to remain from the magnesium sulfate. Now the problem may ask you, what is the limiting reactant? Then the answer is simply, okay, limiting reactant is magnesium sulfate. The problem may ask you, what is the percent yield if this much of this is produced? Then you have the theoretical amount, then you get the actual divided by the theoretical times 100 to get the percent yield. The problem may also give you, for example, if 110 gram of this is produced, what is the percent yield? Then you take this number and 110 divided by 118 to have another percent yield. Okay, so there are a vast amount of information about every component of the reaction that you could compute in grams. Okay, here the case is 180 grams of this sodium sulfate, 484 grams of magnesium hydroxide, this much 3.5 grams of sodium hydroxide, and 0 grams of literally magnesium sulfide can be produced. Remember, for these are the theoretical, and this is the maximum amounts. Okay, if you have a percent yield involved, then you do the kind of calculation that we just showed. Let's wrap it up here. I would actually join you for 1 month session and more problems on limiting reactants as well.